Hello everyone, today we're talking about matrix equations. This is material from 1.4 of the text. So maybe the main idea, first of all, is we're going to want to express linear combinations of vectors, which was the topic of last lecture, in terms of a certain product of, let me put this in quotes, matrix times vector. So we're going to define what it means to multiply a matrix times a vector, and we'll see how actually by definition this is going to be connected to the idea of a linear combination. Let me just start with the definition then. Suppose A is an m by n matrix. So remember, m rows, n columns, and let me call those columns, those are vectors themselves, so let me call them A1, A2 through AN. Okay, so A looks like, A1 is the first column up through AN, and let X, let's say is X1 through Xn, be any vector in Rn. Then AX is the vector, so I'm defining what it means to take A times X, that's what I mean here. This is the vector defined to be, I'm going to define it as the linear combination of the columns of A, so A1 through AN, with weights. Remember, when I have a linear combination, I need weights, so they're going to be the entries of that vector. So you gave me this vector x, it has n entries, those will be the weights of this linear combination. So in symbols, what this means is ax equals, well, I take x1, the first entry of the vector, and I scale a1 by that. I do it for the second column, and etc. The last entry will be, this last vector will be the last entry of x scaling the last column of a. I add those all up, I get a new vector. So I call this like a times x, right? That's what I mean by when I write that, right? This concatenation. I'll show you an example in a second. Let me just note that this makes sense. So AX is defined only if, actually if and only if, the number of columns of A equals the number of entries in X, right? Because I'm making a linear combination, I better have, if I have n vectors, I better have n weights to make this linear combination. Let's do this with an example. I think that's where things become clearer. So let me take A to be this matrix here, times a vector. So this is a matrix A. It's got 3 columns. I better multiply it by a vector with 3 entries. I'll take that. So this will be my A. This will be my X. So what is this? So again, what I do is I take the columns of A, if you like. These will be my vectors in the linear combination. And then I scale them by the entries of this vector X. So like 4 goes there, 3 goes there, 7 goes there. Okay? That's the definition of A times X. I just do this, and I consider this linear combination. Let's actually solve this. So this is going to be, right, as you know, 4 times 1, 0 is 4, 0. 3 times 2 minus 5 is 6 minus 15, plus minus 7, 21. And then I add all those together, and I get, let's see, 10 minus 7 is 3. And then 6 is my second entry. So notice that, what I get here, so A was a 2 by 3 matrix. The thing that I'm multiplying the matrix by has 3 entries. That corresponds to this 3. But the vector that I get out as a product, right, as the result of multiplying these two, has 2 entries, and that corresponds to the number of rows of A. Okay, so the number of columns of A is the vector I multiply by. The number of rows of A is the size of the vector I get out of this process. Okay, great. What can we do with this? Well, let me recall some things from last time. So as we've seen, vector equations are, well, let's say related to systems of linear equations. I mean, in some sense, they're the same, right? They have the same solution set. And that means we can translate it one step further to connect it to matrix equations. And let me show you what I mean by that. So let me take this system here. So let me just go to kind of day one material here. This is a system of 2 equations and 3 unknowns. Okay, so this is a system, right? And how does that relate to a vector equation? Well, remember this is the same, well, has the same solution set as taking a linear combination of, right, these, well, coefficients that I have here. So 2 minus 5 plus x3 equals minus 1, 3 equals 4, 1, running out of room. Okay, so this is what we call the vector equation. And remember, from last time we saw that these two things have the same solution set. Remember the x1, x2, x3 is the unknown here. Same here, and I want to know which numbers, which choice of 3 numbers works. It's going to be the same for both. And now what we can do is we can say, well, we just learned that linear combinations are really just matrix matrix multiplication. So the matrix that I get would be, the entries in the sort of first row here. These entries here. So I'm making a matrix whose, a better way to say it is the matrix I'm making has columns given by, those vectors that are in the linear combination. And then I multiply it by a vector whose weights I see here. So that's going to be x1, x2, x3 equals the right-hand side, which is 4, 1. Okay, so this, if I call this A and I call this vector x, I call this vector b, ax equals b is called the matrix equation. So that's our main kind of definition for today. And let me just point out that again, some things to note here. That first of all, A is just, what is this A that I have here? This is related to the system. A is just the coefficient matrix of the system. And, just another thing to note maybe is that X is the unknown here. Right, this is why it's a matrix equation, right? When I say equation, it's kind of like, solving for the unknown. Now, that's what I mean by an equation. So A is usually given to you, B is given to you. You want to find X. And in this case, X is just a vector of n entries. Okay, and so let me just kind of repeat myself with the kind of general fact here. So this is a kind of important fact for this lecture, is that these 3 things I just talked about are all related in the usual way. So let me set up some notation. Suppose A is an m by n matrix with columns A1 through AN. So again, A is equal to, it's a matrix where your first column is A1, second is A2, etc. And let's let B be any vector in Rm, okay? Then the fact is that the matrix equation now that I get, so the matrix equation is A times an unknown vector equals B, the vector you gave me. This has the same solution set as the vector equation. So what's the underlying vector equation here? It'll be x1 times a1 plus x2 times a2 plus ... xn times an. Right, that's the vector equation. And this has, which in turn has the same solution set as the system. And what's the system going to be? Well, you take the matrix A, I'll write it as its columns, A1 through AN, and I augment that guy with B, right? And this is my system that I'm representing as an augmented matrix. And this is, again, not really anything new. This is more or less translating what we had from last time, in addition to this extra encoding as a matrix equation. So in particular, let me just write this down and I'll finish here. In particular, ax equals b has a solution. So if I only want to know, does it have a solution, this will happen if and only if b is a linear combination of the columns of A, which in turn will be the case if and only if the system A, B has a solution. And the point of all this is that if I ask you if any of these things have a solution, it comes down to asking whether this thing has a solution, and you can determine this by reducing to echelon form. So the point of this the point of this note that I'm making here is that if I ask you whether one of these or any of these has a solution, you do that by considering the system in this augmented matrix, and you reduce to echelon form and do the usual thing. You look for those rows of zeros with something non-zero on the right-hand side. So I'll do an example of that next time. We'll see you then.